Good morning, everyone. So we'll continue talking about game theory. Last time we talked about what kind of games we are discussing, two-person zero-sum games. We discussed some very simple strategies for analyzing such games. The simplest strategy that we discussed was eliminating some of the worst possible moves of the players. So if one move is dominated by some other move, which means if it is strictly worse for any kind of response of the opponent than the other move, well, you should just eliminate it. And then we discussed that, well, in very small minority of games, this is just enough to simplify the game so that it will be possible to analyze it completely. For a little larger class of games, we have a little different strategy, which was about estimating the security level of the players. So the security level, let me remind you, it was, let's say, the first player can he play to guarantee to win at least, say, $1 in every round. If he can, then $1 is his security level. And for player 2, can player 2 guarantee that by playing some move, the first player is not going to get more than $1. If it is true, well then $1 is the security level for player number 2. And let me both remind you what a pair of matrix is and how given a pair of matrix to realize what the security levels of the players are. So last time we discussed the game, it was something like this. Each player has 3 strategies. The payoffs are 2 minus 1, 2, minus 3, minus 2, 8, and minus 2, minus 4. So first of all, let's recall what this table is about. It tells you that the game is played as follows. Each of the players chooses for himself whether he will play strategy 1, 2, or 3. He doesn't announce it, they don't announce it in some particular order, they announce their choices simultaneously. So that no one knows what the other player chose before he gets to make a choice. And then depending on their pair of choices, there is some amount of points awarded. And this is the number of points awarded to the first player. The second player will get the opposite amount. You play a zero-sum game. So for instance, if the first player chooses to play strategy 2, and the second player chooses to play strategy 1, we go here, we see that the first player will get awarded minus 3 points, so he loses 3 points. And respectively, the second player is going to get 3 points. Now, by looking at this table, can you try to guess, is this game good for player number 1 or good for player number 2? If you were to play this particular game, would you play as player number 1 or as player number 2? So both players have some kind of thing going for them. For instance, player number 1 has 2 strategies which he might try to play in such ways to kind of get these large payoffs, 8 points, 10 points. On the other hand, player number 2 also has some very good strategy. He can play in such ways, never lose. Never lose. In fact, at each round he can play so that to get at least 1 point. So even though we have these large payoffs for player number 1, well, somehow he will never get a chance to play in such ways to get these amounts of points. If player number 2 is smart enough, he will play probably strategy number 2 and will prevent player number 1 from ever getting to these good fields. And last time we kind of formalized this idea with talking about security levels for the players. So let's talk about security levels. which are guaranteed by each one of these pure strategies. If player number 1 plays strategy 1, well, then he can be assured that he will get at least -1 points. Well, not that good, but that's the largest he can hope for in any case, regardless of what the response of player number 2 is. If he plays strategy number 2, well, he is assured to get at least -2 points. And finally, if he plays strategy number 3, he is assured to get at least so here he is assured to get -3 points. Player number 2 might respond with strategy 1, and here he is assured to get at least -4 points. So among these 3 evils, he will choose the lesser one, and he will get this amount. So he can guarantee to lose at most 1 point on every round. For player number 2, the security levels, let's recall what they are. It's, let's say, in this strategy. Can he prevent player number 1 from getting at most 10 points? Well, of course he can. Can he prevent him from getting any smaller amount? Well, actually no. If he chooses to play strategy number 1, it is conceivable that player number 1 will play strategy number 3 and will gain 10 points. So here, the security level is 10. He can prevent player 1 from getting more than 10 points. Here, he can prevent player number 1 from getting more than how many points?
He will always win, so it's at most 1 point.
At most,
well, negative
-1. So he can prevent player number 1 from getting more than -1 point. So he can make player number 1 always lose at least 1 point. Yeah.
Why is the first security level 10?
So here, player number 1 can prevent the first player from getting more than 10 points just by playing strategy number 1. Of course, if he plays strategy number 1, player 1 will get at most 10 points. However, he cannot prevent him from getting, say, more than 8 points, or more than 9 points. It might happen conceivably that if he plays strategy number 1, player 1 responds by strategy number 3, and player 1 does get 10 points. So, just to remind you, the security levels for player number 1 and player number 2 are defined a little bit asymmetrically. For player number 1, it is the minimal payoff that he can guarantee for himself. For player number 2, it's the maximal payoff that he can prevent the other player from getting.
Oh.
So here, he can prevent player number 1 from getting more than 10 points. Here, he can prevent player number 1 from getting more than -1 points. In other words, he can make him lose at least 1 point. Or here, he can make him get less than or equal than 10 points. And here, well, he can make him get less than 8 points. So if he plays 3, he will make the other player get at most 8 points.
So it's basically like the worst possible payoff that player 1 can have, the second person.
So it's, from the point of view of player number 2, it is the worst case scenario, yes. Similarly for player number 1, it is the worst case scenario for him. But here we list, but in both cases, the agreement is to list the payoffs for player number 1. Because later we'll compare these numbers and these numbers, so they better be about the same thing, about the payoff for player 1.
Okay.
But in both cases, you're right, it is about the worst case, from the point of view of each of these players. Okay, so now we look at player number 2. He wants, of course, the first player to get as few points as possible, and he will choose this strategy, because it guarantees that player number 1 will lose at least one point. Well, and player number 1 can play so that to lose no more than 1 point. So once both players realize their opportunities and their restrictions. So the opportunity, let's say, if player number 1 is to lose no more than 1 point, and the restriction, he knows that player number 2 does have a strategy which will lead him to lose at least 1 point. So the best choice for him is to actually play for getting this minus 1 point. For player number 2, well, he can make the first player lose at least 1 point, but he cannot make him lose more than 1 point, because player number 1 does have a way to lose no more than 1 point. So he also chooses this strategy. So in this game, we just know that every round will be equally important. If both players are smart, if both are rational, have the computational resources to understand everything about this game, every round will look exactly the same. Player number 1 chooses strategy number 1, player number 2 chooses strategy number 2, and player number 2 wins 1 point. So, it's not a very exciting game to watch. So let's now talk about, so maybe before this, any questions about these security levels? So of course, in every kind of matrix game, you can analyze these security levels. Just the numbers on the right are the smallest numbers in each of the rows. The numbers on the bottom are the largest number in each of the columns. And well, then you take the smallest number among these numbers, the largest number among these numbers. If they happen to do the same thing, then you are done. You know you are playing one of these boring kind of games. Well, luckily for us, I mean, we do want to have some fun. There are games which are not boring. And let's talk about a game which is called Matching Coins. So the rules of the game are as follows. You have 1 or 2 coins in your pocket, and you choose whether to play 1 coin or 2 coins. And then the other player also has he has 2 coins, and he chooses to play either 1 coin or 2 coins. If the numbers of the coins that you both play are the same, you get all the money. If the numbers are different, the other player gets all the amount. So let's talk about this game in terms of payoff matrix. What are the possible strategies? Well, you can play either 1 coin or 2 coins. So you have just one choice to make, whether to play 1 coin or 2 coins. Same goes to the second player. If the number of coins that both of you choose is the same, so 1, 1 or 2, 2, you will get all the amount which is on the table. So player number 1, in this case, gets 2 coins, in this case, gets 4 coins. If the number of coins is not the same, 1, 2 or 2, 1, the other player gets all the coins. So we are playing this kind of game. Okay, so first of all, is this game one of the boring types like this? Is there a strategy which is obviously better than other ones? Well, let's see. Let's compute the security levels. So player number 1, if he plays strategy number 1, is guaranteed to lose no more than 3 points. If he plays strategy number 2, he is guaranteed to lose no more than 3 points. Okay. What about player number 2? Well, he can guarantee that player number 1 will get no more than 2 points by playing strategy number 1. He can guarantee that player number 1 will get no more than 4 points by playing strategy number 2. So his security level is 2. For player number 1, it's -3. So there is quite a difference. First player can play so in such a way as not to lose more than 3 points. Second player can prevent him from getting more than 2 points. Well, somewhere in between will be what will happen actually. I mean, it's clearly not a good idea to just choose a strategy and announce it to your opponent. Just choose to play 1 coin and tell, I am playing with 1 coin. Well, that will be a disaster. If you say, I'm playing with 1 coin, your opponent will choose the best strategy for you, you'll lose 3 coins. Okay. So this game is, well, not boring. In the sense that every round should not look the same. Because first player will have somehow to randomize. Like in rock, paper, scissors, the best strategy is actually to randomize your choice. It's not always play rock, not always play scissors, somehow randomize. So this game seems to have some kind of, well, something interesting going about it. So maybe before we analyze this game completely, I want to check your intuitions. So I'll ask you to make up your mind about the following thing. If you were offered to play this game, would you rather play as player number 1, as player number 2, or you think that it's the same thing? I mean, the average payoff is kind of 0 to each player, something like this. So once again, I want each one of you to decide if he or she were to play this particular game. The rules as follows. Each one of the players choose a number, 1 or 2. If the numbers are the same, the first player gets the sum of the 2 numbers. If the numbers are not the same, the second player gets the sum of the numbers. And my question is, if you were offered to play this game, would you think it is equally good for player number 1 and player number 2? Or you would rather play as player number 1? Or you would rather play as player number 2? So let me take a vote. So how many of you think that this game is equally good for player number 1 and player number 2? 1, 2, 3, 4, 5, 6, 7. How many of you would rather play this game as player number 1? The one who gets equal amounts of coins. How many would play this game as player number 2? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Okay. And can anyone tell me about his intuitions? Maybe does anyone have any kind of explanation for his or her intuitions about the actual choice? Yeah.
I was thinking they're equal because, well, out of 4 times, let's say all those 4 events happen equally. Then 6 points is for number 1, 6 points for number 2.
Mm-hmm. So the intuition for this kind of choice was, well, the sum of payoffs to player number 1 seems to be 6, for player number 2 seems to be 6.
Yeah.
So depending on who wins, well, if they are roughly kind of same frequency, all these outcomes, then maybe it is kind of the same thing for player number 1 and player number 2. Okay. Can I get some intuition for why player number 2 will win? So player number 2 is the player who will get the different amounts of coins. So if the amounts of coins are different, he will get three coins. So what are the intuitions behind this choice? Yeah?
Player number 2 wins, then he is guaranteed to get more than 2 points. So, because if player number 1 wins, and they both played just 1 coin, then he would only get 2 coins, right? But if player number 2 wins, he would get 3 coins regardless. So, I think it's fair.
Okay, so if I understood this intuition correctly, the intuition was, well, player number 2 is guaranteed, well, I mean, whenever he wins 3 coins. Player number 1 sometimes gets 2 coins, sometimes 4 coins. So maybe it's reasonable that player number 2 will be able to make his strategy in such a way as to guarantee that player number 1 gets 2 points more frequently than 4 points, and then he wins. Was it about the right explanation?
Yeah.
Okay. Any other intuitions, any other explanations? Is there anyone who wants to change his mind? I don't care about from where to where, just change his mind. Okay. Okay, so let's try to analyze this game mathematically, and we'll see what actually happens. So let's try to analyze some particular kind of strategy. Let's analyze the strategy for player number 1, which is as follows. Take a coin, flip it. If it's heads, play strategy 1. If it's tails, play strategy number 2. So with probability 50-50, choose either 1 or 2. Let's see what will happen there. So let's discuss strategy for player 1.
So it's completely there's no bias, like 1 and 2 are just equal probability?
Yes. So when I say strategy, it is about deciding in advance what you are going to play. So play in such a way that if you kind of announce the strategy to your friend, he will be able to play instead of you exactly as you would play. So one possible strategy, I'm not saying that this is the best strategy. Just one possible strategy is to choose completely at random with equal probabilities to choose either 1 or 2. It is one possible strategy. Let's just see where it leads us, whether we can win by just using this strategy. So because this strategy is not kind of pure, we are not announcing we are going to play 1. It's about a choice of random choice. It's called a mixed strategy. So mixed strategy for player number 1, one possible such strategy. 50% of time choose 1, 50% of time choose 2. Let's see what kind of expected payoff, what kind of payoff we should anticipate for player number 1 once he makes such a move. So when I say expected payoff, I mean if he repeatedly plays a strategy, let's say for 10 rounds, the same strategy. If he plays it for 10 rounds, he will get, well, on average, such and such number of coins. So this number of coins divided by 10 will be his expected payoff for 1 round. So let's see what will happen. Of course, the expected payoff to player number 1 does depend on what is the response of player number 2. If the response of player number 2 is strategy 1, then what happens? Let's suppose that player number 2 responds by choosing strategy number 1. Well, half the times player number 1 will get 2 points. Half the times he will get minus 3 points. So overall, each time he's going to get the expected value of 1/2 of this thing minus, well, plus 1/2 of this thing. So it's 0.5 times 2 plus 0.5 times minus 3, which is 1 minus 1/2. So at least on the rounds when player number 2 responds by playing strategy number 1, what should you expect to happen? Well, you should expect that if you play 10 such rounds, on average you will get minus 5 points overall. If you play 100 such rounds, where player number 2 responds by strategy number 1, you should expect to get minus 50 points. It's a little bit meaningless to say that by playing just one round you should expect to get minus 1/2 point, because, well, you never get actual minus 1/2 point. But if you repeat this strategy over many times, let's say you play this game 1,000 times, then what you should expect is on 500 of these rounds you will get 2 points, so overall you will collect 1,000 points from these rounds. On the other 500 rounds you will get minus 3 points. So you will lose 1,500, and overall you will lose 500 points. Well, if player number 2 plays strategy number 2, so on the rounds when player number 2 chooses to play strategy number 2, you should expect to get minus 3 times 0.5 plus 4 times 0.5. So it is 1/2. So if you play, say, 1,000 rounds where player number 2 responds by choosing strategy number 2, you should expect to get at least 500 points. Well, of course, player number 2 can also mix these strategies. You are not guaranteed that by playing 1,000 rounds, player number 2 will always respond by strategy number 2 or strategy number 1. Of course, he might also mix these strategies. But then you will get some kind of average of the one proportion you will get minus half times this proportion, from the other, from the complement of this you will get half of the complement. So you will get some kind of weighted average of these pairs. So depending on what kind of mix of strategies player number 2 responds by, you'll get anywhere between minus half point and 1/2 point on each round. In fact, if you just announce your strategy to player number 2, you just pre-commit to playing only this strategy. So you tell him, you know what, for the next 1,000 rounds, I will only play this particular strategy. And you kind of guarantee that you will not employ any other kind of strategy. What is the rational response of player number 2 in this case? Well, he can do better. If he does the same, if he chooses to mix between strategy 1 and strategy 2, what is going to happen is, in equal proportions. Half the rounds he will get half the point, half the rounds he will lose half the point, and on average he will get nothing. But of course player number 2 can do much better. Choose strategy number 1 always. Yes. So if let's say I play against you, and if I pre-commit in the next 1,000 rounds to choose this strategy, on every particular round I'll take a coin, flip it, see whether it's heads or tails, according to this decide whether I'm going to play 1 or 2. Your rational response is always play strategy 1 against me? Well, because then I'm expected to lose 500 points in the next 1,000 rounds. It's not rational for even any round to choose response number 2, because you're expected to lose 1/2 of the points. So you're expected to get less points. So by choosing to play strategy number 1 against such kind of player on every round, player number 2 is guaranteed an expected payoff of 1/2 a point for every round. So in fact, this strategy does lead to a win for player number 2. Okay. So the only thing that this shows is it's not a good strategy for player number 1. I mean, it is much better than just announcing that he will play strategy number 1 always, because then he loses 3 points in every round. But, well, he still loses 1/2 a point. Can he do better? Can he lose less? Can he perhaps win? So let's see. The reason we get this -1/2 over here is because, well, this outcome of 2 happens, well, quite rarely, only half the times. But the other half the times we lose 3 points. So maybe it's a better idea to try to make this outcome of winning 2 points more frequent. And then we'll somehow make this number not negative, which means the other player has a choice of strategy, so that we will always lose. Well, not always, but on average we will lose. And then maybe it will work somehow. Maybe we will win some amount of money every turn. Well, on average every turn. So maybe let's try to increase the probability of playing strategy number 1 over here to make this number positive. Maybe this will work. So let's analyze some other strategy. So for now I don't want to get too precise. Maybe any suggestions for probabilities for choosing strategy 1 and strategy number 2. So I know that if I choose strategy number 1 even less frequently, I will lose even more points. That's kind of guaranteed, because then player number 2 will continue to play strategy number 1 and I'll keep losing points. So I want to increase the probability of playing strategy number 1. So maybe any suggestions for number? I know 100% is not good, because then I'm still going to lose 3 points in every round. So somewhere between 50 and 100. Just give me a number. Kind of round number so that I'm able to actually compute. 75. So let's continue such a strategy. So if 3/4 of the time we'll choose strategy number 1, 1/4 of the times choose to play strategy number 2. What's going to happen? Well, so we'll get the expected payoff of 3/4 of the time we'll get 2 points, 1/4 of the times we'll get -3 points. So on average we are going to get a -3/4. So 3/4 of a coin. Okay, this sounds really good. So on the rounds when player number 2 chooses to play against us strategy number 1, we are expected to gain 3/4 of a coin. Let's see what happens on the rounds when player number 2 responds by choosing strategy number 2. So we are expected to get 3/4 times -3 plus 1/4 of the times we'll get 4. So quarters minus 9 quarters minus 5 quarters. Oh no. So on these rounds, we are going to lose on average 5 quarters of a coin on each round. So in this case, if we pre-commit ourselves to playing this strategy, well, the rational response of player number 2 is just always responding by playing strategy number 2. In this case, he'll, on average, on every round, gain 1.25 coins. So it seems that this strategy is also not good. But it's not good in slightly different way. So this strategy was not good because our opponent could respond by playing strategy 1 against us. This is not good because the other player can play strategy number 2 against us. Well, next idea is maybe we can still mix between these two strategies. Maybe we can get some kind of probabilities in between 1/2 and 3/4 so that the other player will not know which strategy is better, strategy 1 or strategy 2. I mean, if one of these strategies is better for him, he will choose it. Well, it seems that we are going to lose. So maybe we'll try to find some probability in between 1/2 and 3/4 so that the expected payoff, such kind of thing, will be the largest for us. So the next idea is, let's stop guessing. Let's analyze the most general strategy. X1 probability, choose 1. This probability is 2%. Well, this will be actual numbers. This probability X1, I mean X1 could be say 0.5, which will correspond to this strategy. Choose strategy number 2. We want X1 and X2 to add up to 100%, so we want one to be the complement of the other. And let's see what are the expected payoffs. So on the round, when player number 2 chooses to play strategy 1, we are expected to get 2x1 minus 3x2 coins. On the rounds when player number 2 chooses to play strategy number 2, we are expected to get minus 3x1 plus 4x2 coins. Now, of these two numbers, well, one of them is smaller, and we want to choose the largest possible value of this smaller of these two numbers. So, let me formulate it like this. I want to make sure that 2x1 minus 3x2 is bigger than some number. This will be my mixed security level. I want to make sure that the other strategy also gives me a payoff of at least this number. And I actually want this payoff to be as large as possible. So I want to maximize S. So what I want to do is, once again, I want to guarantee that the expected payoff both here and here is larger than some number. So like here, this number would be minus 1/2. Well, I don't want to settle on just 1/2, or rather minus 1/2. I want to get the largest possible expected payoff for myself. Under the conditions, well, this condition, this condition, this condition, all of these are probabilities. About S, I don't know that it's positive. I'll try that S is a free variable. So now I just told, well, I told you what I want. I want to choose the probabilities x1 and x2, which will maximize my expected payoff. So once I choose to place probabilities x1 and x2, my expected payoff is some number which is smaller than both of these. Okay. But now, well, the catch is that this problem is a problem that we know how to solve. It is a linear programming problem. It is about maximizing the quantity subject to some linear constraints. Maybe let me rewrite it closer to the standard form. So maximize S in such a way that 2x1 minus 3x2 minus s is positive, minus 3x1 plus 4x2 minus s is positive, x1 plus x2 is equal to 1, x1 positive, x2 positive, s is 3. Could be positive or negative. Well, unfortunately, we did not discuss when we discussed simplex algorithm, we never treated free variables, so we never allowed some variable to be either positive or negative. Well, so I don't want today to talk about the congruities. I don't want to go once again over simplex algorithm or introduce some kind of technical ideas. I want to understand some ideas about gate theory. So at home I just gave this problem to Lindo and gave me the following output. X1 is 7 over 12. X2 is 5 over 12. The payoff is minus 1 over 12. So this is the output from Lindo. It tells you the following information about the game. If you are forced to announce your strategy in advance, which means you have to decide on this strategy. I will play strategy number 1 with such and such probability. I will play strategy number 2 with such and such probability. And I'll keep my promise for the next 1,000 rounds. Then the best choice that you can make is to announce the following strategy. On 7, well, with probability 7 out of 12, I'll play strategy number 1. With probability 5 over 12, I play strategy number 2. On average, I will lose 1/12 of a point. So if I will play 1,200 rounds, I will lose 100 points. So, first of all, it's not bad at all. All of the previous strategies, well, the naive strategies, pure strategies, we're losing 3 coins in every round. Which means if I play 1,000 rounds, I lose, well, 3,000 coins. This strategy loses half a coin every turn. So 1,000 rounds, loss of 500 coins. This optimal strategy loses just 1/12 of a coin. So I play for 1,000 rounds, I lose only, well, 85 coins, something like this. So this strategy is actually not that bad. It is still losing, but it's not that bad. So next question. Here we saw this a problem which was actually a little bit unfair to us. we thought about the process in the following way. We will play some kind of game where we actually announce our strategy in advance. And we let player number 2 use this information to decide on his strategy. So we always expected the worst kind of behavior of player number 2. But of course, in the actual game, player number 2 doesn't have the information. He doesn't know what probabilities I chose. I choose them for myself in secret. I don't announce them. So maybe there is a way to exploit this kind of thing and play in such a way as, well, depending on how the other player is playing, to choose the probabilities a little higher, a little lower, maybe some kind of tricky thing like this, and still get a positive payoff for ourselves. Maybe there is a way to push this strategy a little more. Well, not quite obvious. I mean, it's not easy from just observing the behavior of the second player to understand what kind of strategy he is using and how to exploit it. So if he plays strategy number 1 in the first 300 rounds, it would mean quite a lot of things. Maybe he's pre-committed to always playing strategy number 1. Maybe he's pre-committed to playing strategy number 1 on the first 300 rounds and then switch to strategy number 2. Or maybe, well, he made 300 always random decisions and always chose strategy number 1. This is very unlikely, but still a possibility. So we found a strategy which guarantees us that we lose no more than 1/12 of a point on average in every round, regardless of the response of player number 2. Okay. Is this strategy actually the optimal one? In the boring kind of games, once we found a strategy which always guarantees for us a loss of, say, no more than 1 point, we asked ourselves the following question. Can the other player play in such a way that we will always lose at least 1 point? If he can, well, we know that we don't have any better choice. So that's the question we want to ask ourselves now. Does player number 2 have a strategy which will always lead to our loss of 1/12 of a point on every round on average? So you seem not to believe that he does. Okay. So let's discuss strategies for player number 2. So strategies for player 2. Once again, let's start with discussing kind of naive strategy of playing 50% strategy 1, 50% strategy 2. We know that on some rounds player number 1 is going to play strategy number 1, in some rounds he'll play strategy number 2. Let's see what will be the expected payoff. Let's say to player number 1. So here will be expected payoff to player 1. So, in this case, so if player number 1 chooses to play strategy 1, half the dice will get 2 points, half the dice player number 1 will get 2 points, half the dice will lose 3 points. So on average, it's going to get 2 times 0.5 minus 3 times 0.5 minus 1/2 point. So this outcome is actually good for us, good for player number 2. That's the expected payoff to player number 1. If player number 1 loses, player number 2 wins. But what if player number 1 responds by playing strategy number 2? Well, he will lose 3 points half the times, but he will gain 4 points another half the times. So on average, he'll get 1/2 of the point in each round. This is not good for us. So if we play this strategy, we know that on the rounds, when player number 1 chooses to play strategy number 2, he will get 1/2 of the point, and we are going to lose half of the point. So this mix of probabilities is, well, not terrible, but also not very good. If player number 1 somehow can read our mind, if he knows what our thought process is, if he knows that we are choosing with 50% probability, he will be able to exploit us and win on average 1/2 of a point. Okay, so let's not continue guessing in this case. We now know what is the general procedure for deciding. Let's assign a strategy with probability y1 for choice of strategy number 1 and probability of y2 for choosing strategy number 2. What is the expected payoff for player number 1? Well, 2 times y1 minus 3 times y2 in this case, minus 3 times y1 plus 4 times y2 in this case. Now we want, what do we want from these numbers? We want the largest of the 2 numbers to be as small as possible. So we want to make sure that both numbers are smaller than some other number. So our new problem is to make sure that both numbers, 2y1 minus 3y2, are smaller than some number. Let me call it security level for player number 2. Minus 3y1 plus 4y2 is both security level for player number 2. So I want to make sure that both of these payoffs are smaller than some number. And I want the smallest one. I want to choose a strategy which will lead to the smallest expected payoff for player number 1. And of course, I want y1 and y2 to be probabilities. So still I want y1 plus y2 to be equal to 1, y1 to be positive, y2 to be positive. But S2 can be whatever, positive or negative. So we get this kind of linear programming problem. It is a little different from the first one. First of all, the variables have different names, but also here we want to minimize something, the inequalities are in the opposite direction. So it is not the same.
Do we know how to solve these types of ones?
So for now, no. We'll discuss next time how to deal with 3 variables. And for now, we'll just give it to Lindo and let it solve. So in Lindo, if you want to make a variable free, just in the very end of the file, just say free, and then the name of the variable.
This is just a dual of the. This is just a dual of the first
Yes.
algorithm.
Yes. In fact, it is a dual. But for now, let's just treat it as a problem and find out the answer. So answer y1 is 7 over 12, y2 is 5 over 12, s2 is minus 1 over 12. So let's think about this thing. It says that if we choose the probabilities in such a way, 7 over 12 and 5 over 12, 7 over 12 for playing strategy 1, 5 over 12 for playing strategy number 2, we will guarantee that on average, player number 1 will lose 1/12 of a point. So there is no way for player number 1 to get more than -12 of a point on average in every round. So just by playing these particular probabilities, we will guarantee that regardless of what the other player plays, strategy 1 or strategy 2, he will always lose 1/12 of a point.
So there is a better strategy for him than just not play the game at all.
Yes, so that is what the rational agents will actually do. But you know, in this class we have 7 people who would agree to play this game. So, as either player. So, on average, 3.5 as player number 1. Well, the equality of these security levels for player number 2 and for player number 1, maybe it's better to use the name security level player number 1, tells you that this game, well, is not boring in the deterministic kind of way, but it is boring in this probabilistic kind of way. The first player, for him, the best possible strategy is to play with these particular probabilities. For the second player, these particular probabilities. On average, we can just predict the outcome. If there are 1,200 rounds played, well, player number 2 will win 100 points. If player number 1 decides to choose another kind of mix of strategies, well, he'll lose more points. If player number 2 decides to choose a different kind of strategy, he'll gain less points, maybe even lose some points. But if both pursue the same strategy, they both know that, well, it's the best thing for them. Player number 1 can play in such ways to lose no more than 1/12 of a point on every round, but player number 2 has a way to make sure that he loses at least 1/12 of a point on every round, on average. So this idea, this game, first of all, it is not fair. Player number 2 is expected to win. Another thing, yes, it is not fair, but I mean, if I were playing against another human, I would actually play as either player 1 or player 2 because, you know, 7 over 12 and 5 over 12, for me at least, are not distinguishable from 1/2 and 1/2 as probabilities. I mean, I don't have a random number generator in my head which will generate kind of these probabilities. So, if I play against another human, well, yes, I do know that as player number 1, I'm going to lose if the other human is capable of generating perfect probabilities every time. But if I also know that he didn't analyze this game, and also somehow I know, well, how to exploit the strategy of 1/2 and 1/2 as player number 1, because I know 1/2 and 1/2 actually loses to player number 2. Well, then I will actually play. Against the computer, well, never. Or against a human who analyzes this game and actually takes a coin and finds these probabilities, 7 over 12 and 5 over 12, also never. But this game is, well, quite subtle. So it's the kind of game that you might be offered in a casino. You are expected to lose, but on average by small amounts. With some kind of streaks of luck, streaks of bad luck, on average you're going to lose small amounts. So one lesson from this game is, well, first of all, a game which might look kind of innocent and fair might actually not be quite fair, at least for one of the players. Especially if one of the players had the time to analyze this game. Another thing is, we can analyze these games using this simplex algorithm, at least in the case when the two problems give the same answer. Third thing, we'll discuss this thing in general next time, but for now, just look what happens. The coefficients in these two problems, this problem and this problem. In one of them we took the columns, in the other one the rows of this matrix. In one of them we are maximizing, in the other one we are minimizing. Here we have signs greater or equal than, here we have smaller or equal. These problems are in fact dual to each other. So the problem of deciding on the security level of player number 1 is dual to the problem of deciding the security level of player number 2. From the general duality theory, we do know that the optimal values should coincide. It's not a coincidence that they coincide. We know that the answer, the optimum answer to both, to the pair of dual problems is always the same. So it's not a coincidence that we get the same answer here.
So the fact that the matrix is symmetric has no effect on the fairness of the game?
No. So we'll talk a little bit more. I mean, the fact that matrix is symmetric is responsible for the fact that the strategies of the two players, the optimal strategies, are quite symmetric. Each one should choose their strategy with probability 7 over 12. But it's not what is responsible for the fact that this game is kind of probabilistically boring. In fact, every matrix game is probabilistically boring. It comes from just duality theory. The reason I'm not going into discussion of duality right here, right now, is because it is in a class of problems which we never treated. We never let some variable to be free, so we don't know how duality works with such things. But I might as well tell you that there is a way to extend duality to these kinds of problems, and this pair of problems is dual to each other, and the duality theory does guarantee that the objective functions are the same in these cases. Okay, but today, instead of discussing these theoretical details, I want to introduce another kind of game, which is, well, it is a model for poker game. So it will be a poker game, but extremely, extremely simplified. And the point of introducing this game is, well, not for the sake of making a few extra calculations like this, but really for the sake of giving you the impression that you can actually solve the actual poker game. Well, in some sense. So let's discuss the rules of the new game. Maybe so the game develops as follows. There are two players, Aries and Bob, and Aries and Bob, Anti, and one Bob. Second step is Aries gets a red or a black red, 50% black. So one card is dealt to her out of the deck. It's 50% times red, 50% times it is black. Then she decides either to fold or raise the ante by $1. Fourth step, Bob has to decide whether to fold.
What's the colors involved? And what's the first thing? Colors involved?
Ante. So they pre-commit to playing at least $1. Yes. I think it is a word.
It's ante when you, like, it's ante when everyone at the table first has to put in some certain amount before they even see their whole hands.
Yes, that's exactly the thing. So they both pre-commit to playing at least $1, so they put $1 on the table. Then Alice gets one card, it's either black or red, with equal probabilities. Then she decides either to quit the game, so in this case she loses her ante of $1 and she gives it to Bob, or to raise, to put another dollar on the table. Then Bob has to decide. Yes, she does see her card. So then Bob decides either to quit the game or call, which means also put another dollar on the table. And finally, so this was the bidding stage of the game, and finally we have if both players play, are playing. So there is of course a chance that one of the players actually quit the game before this stage, and then the game is decided already. If both players are still playing, so if Alice raises and then Bob calls, then they check whether Alice has a red card, red or card. So if Alice has a red card, she gets the bottom. Otherwise, Bob gets it. So let me kind of simulate this game, at least a couple of rounds of this game, so that you all know that we understand what the rules are. So we have Alice over here, we have Bob over here. Alice is dealt a card, she can see the card. Well, first of all, both put $1. So now the pot is $2. Alice is dealt a card, it's either red or black. Let's say it is red. She can see her card, Bob cannot see her card. So Alice looks at her card, she sees it's red, she decides, let's say, to play. If she wants to play, she must put another $1. Then Bob, well, has to decide whether he wants to continue playing, in which case he'll have to put his dollar on the table, or to fold. Let's suppose he folds. If he folds, the game is stopped right now, and Alice gets all $3. So overall, she won $1, the dollar that Bob put. If Bob decides to call, then he has to put $1, and then Alice has to show her card. If it is red, which in this case it is, she gets the $4. So now she won $2 that Bob has put on the table. Let's see what happens if she gets a black card. So on the first round, so she has put $1 and $1. She has a choice, either to fold, in which case she doesn't continue the game. She has to be, Bob gets all the money, so Bob wins $1. She might also decide what's called to bluff. She might want to continue the game, hoping that Bob will actually fold and give his dollar to Alice. So she might continue the game, in which case she puts $1, and Bob has to make a decision, either to fold. Remember, he does not see the card that Alice is holding. So if he folds, he loses $1, but if he calls, he'll put $1, Alice will reveal her card, it's not red, Bob gets $2 from Alice. So that's how the game is played. And the question is,
doesn't Alice have to take advantage of this?
yes, she does.
For half the time she's guaranteed of winning at least one.
Yes. So she does have an advantage. On the other hand, I mean, if Bob is somehow seeing her card, sees her card, if she has a mirror behind her, then she actually is, well, at a disadvantage. Every time she wants to bluff, she will have to lose $1. So basically, there is kind of only one losing strategy for Alice, and yes, she does have a huge advantage. She more or less never loses money, except the times when she decides to bluff and Bob calls on her bluff. The question is, how big is her advantage? And also, should she ever bluff? Should she, maybe one possible strategy is to always play honest. If you get a red card, raise $1, and let's see what the response of Bob is. If she gets a black card, just never play. Isn't the best strategy. Should she sometimes, maybe in order to somehow fool Bob, maybe she should just, how's it called, underbid. If she gets a red card, maybe it is rational for her not to put $1 extra, because if she always kind of gets a red card and then puts $1, then Bob will eventually know that every time she puts $1, she probably has red card or something like this. Maybe sometimes she should underbid. So the question is, what is the strategy which will allow Alice to maximize her expected payoff, regardless of the strategy of Bob? Well, let's try to construct the payoff matrix. Now we have two players, Alice and Bob, and they have to make their choices. So both choices are very simple. She either calls or folds. The choice that Alice has to make is more complicated. So she doesn't just make a choice of put $1 extra or fold. She has to make more complicated choice. I mean, it's not true that if I were Alice and I were to communicate my strategy to somebody to play instead of me, I would just say, you know what, regardless of what you get, always fold. That would be stupid. Another strategy is kind of, regardless of what you get, always raise $1. Also stupid. I want to make my decision based on what card I see in front of me. So my strategy as Alice would be described as follows. What happens if I get a red card, and what happens if I get a black card? And I have some options. I can say, yeah.
If you raise it, regardless of what you have, whether like the minimum you're gonna win is still right?
Yes, that's true.
Yeah.
But there is a way to get more than 0.
Yeah.
So we'll see what the outcomes are.
So like Alice wins all the time then.
Yes, so she has a way never to lose. And indeed, if she raises $1 each time, she will never lose. On average, I mean, half the times she will lose $1, half the times she will win $1. On average, she's not going to lose. But there is a way for her to guarantee for herself a victory. A win of some amount of dollars every time. So her typical strategy is described as follows. She doesn't know what she's going to get. So if she were to describe her strategy to a stranger who is going to play instead of her, she would describe it as follows. If you get a red card, let's say fold. If you get a black card, let's say fold. So this strategy describes fold regardless of whatever you see in front of you. Another strategy is if you have a red card, fold. If you have a black card, raise. Another strategy, if you have a red card, raise. If you have a black card, fold. And finally, there is a strategy of you get a red card, raise, black card, raise. So raise regardless of what card you see in front of you. For each of these strategies, we have a way to compute the expected payoff. So let's compute it. Let's say this strategy, which is fold always. If Bob responds by folding, well, sorry. In this strategy, Bob never gets to make a decision, so we always lose $1. So that's the payoff. This strategy, more interesting. I will fold on red, and I will actually raise on black. It doesn't sound like a good strategy, so let's see what the payoff is. So, suppose that Bob decides not to continue the game. So, half the times, Alice gets a red card, folds, loses $1. So, half the times, she loses $1. The other half of the times, she gets a black card, she raises, Bob folds, she wins $1 from Bob. So, this happens when Bob folds. What if he calls? So, half of the times, Alice is going to get a red card. If she folds, in this case, she's going to lose $1. On the other hand, half of the times she'll get a black card, she will raise, so now she has $2 on the table, Bob calls, she loses $2. So this 1/2 minus 1 minus 1/2. Oh, minus 3/2. It's minus 1/2 minus 1. Yes. So in this case, on this strategy, she might lose actually. This strategy, the honest kind of strategy. You see a red, you raise, you see a black, you fold. So what's going to happen? If Bob decides to fold, well, half the times you get a red card and you get $1 from Bob. One half of the times you get a black card, you fold, so you lose $1. On the other hand, if Bob decides to call, what happens is half the times you get a red card, you actually raise to $2, Bob calls, you win, and then half the times you win the $2 from Bob. Another half the times you never get to this stage, you actually get a black card, you fold, you lose $1. So the expected payoff is 3 halves. And finally, the strategy of raising always. So raise on red and raise on black. Half the times, if both folds, half the times you get. Sorry, if both folds, you're always getting the $1 from him in this case. Because you raised both folds, you get $1. So it's okay.
In the previous line, I think it should be 1/2. In the far
This
right.
one, yes, yes. And finally here, it is, so half the time she gets red card raises, he calls and she gets $2. Half the times she raises, he calls, she loses $2. So, unfortunately, we don't have time to finish analyzing this game, but please do remember it until next time. And next time we'll start with recording the game, what the game is, what is the payoff matrix, and we'll finish analyzing. And please take some pictures.